Hello, good evening. Welcome to the Biochemistry series third live streaming. So thank you very much for dropping by. Again, I welcome you to the Biochemistry series channel. Okay, I set up this channel hopefully to make biochemistry a little easier to understand for most by uploading curated videos, live streaming reviews like what we're going to have tonight, and maybe offering some study tips. Uh, I'm Dr. Noel Martin Bautista. No, I'm Doc Bao for short. I'm a retired professor. I used to teach biochemistry for 25 years. And what are we going to review tonight? When I was a student and I experienced this, a lot of students were asking me before to explain or to repeat the lecture or even the SGD, for amino acids, particularly this challenging, okay, challenging part of amino acid chemistry. It is your ionic properties of amino acids. So again, um, can you comment where you're coming from? No, I'm streaming live from Quezon City. Okay, so we have how many? No, we have 5 million. We have 5 billion viewers. It's okay. No, it's okay. Anyway, this lecture will be recorded. Okay, so I think we're going to start, no? So the other viewers will just to follow. Sige, no? I'll make my slide bigger and me smaller. Okay, again, welcome to the live streaming review of your ionic properties of amino acids. I'm Doc Bao, and I'm happy to be with you tonight. This is a very challenging topic, no, because it's really complicated and it's complex. So to start with, what are amino acids? We know very well that amino acids. We'll start from the basics, okay? Then we'll just slowly build up, no, to the more complicated parts because we really have to go into chemistry to really understand this. Okay, so amino acids are basically what? No, they're carboxylic acids. Okay, and they have they're amino. No, they're the amino group of your carboxylic acids. Wait, okay. So this is your generic structure of all your amino acids. You have a chiral carbon. No? It's chiral because just like the hand, no, chiral came from the Greek word kairos, meaning a hand. You have different fingers that is attached to your palm. So here we can see that your amino acids have four different substituents. Okay, at least 19 of the 20 at least now have four different substituents. You have each amino acid will have its carboxyl group, will have its amino group. They are attached to your alpha carbon. Okay, this is your alpha carbon. This is not carbon 1. Carbon 1 is always the carboxylic carbon. So this is carbon 1, this is carbon 2, but this is your alpha carbon. The alpha carbon is the carbon that is attached to your carboxylic carbon. Okay. Then aside from that, you have your hydrogen. No, these three substituent groups, they are present in all your amino acids. But what will confer uniqueness, no, or differences in their properties, in their behavior, no, during titration will be the side chain. You know very well that 19 of the 20 will have four different substituents, but you know that glycine does not have a chiral carbon, no, because the R group of glycine is H. Before we go, no, to discussing the ionic properties of amino acids, you know you have heard of the term ampholytes. Now, ampholytes, or in short, it's short for amphoteric electrolytes. Amphoteric electrolytes. Because what are ampholytes? What are amphoteric electrolytes? They can act as an acid and at the same time they can act as a base. But Doc, what is an acid? What is a base? So we cannot really escape this. Now we really have to understand the concepts of acids and bases that is based on your Bronsted-Lowry, no, Bronsted-Lowry theory of acids and bases. Okay, so in this case, acids and bases are different in a way if in the way they interact with your hydrogen ion or basically your proton. So theoretically, a Bronsted-Lowry acid is a moiety that can donate a hydrogen ion or a proton. No? That's the simplest, that's the shortest definition. Okay, a Bronsted-Lowry acid is a moiety that can donate a hydrogen ion. Okay, that can donate a hydrogen ion. On the other hand, what is a Bronsted-Lowry base? A Bronsted-Lowry base is something that will accept the hydrogen ion. And both of these, no, your acid and your base are present in your amino acids. Okay, by the way, your acid will eventually become your conjugate base of the acid, no, and your base will eventually become the conjugate acid of the base. Now, this is important when we're dealing with buffer later on. Okay, so in this case, no, what we saw a while back is your unionized amino acid. It is good only in paper. Okay, again, you have your alpha carboxyl group and you have your alpha amino group. Okay, so your alpha carboxyl group, you know that you have the hydrogen, then you have your amino group. So in solution, you know that in solution you have water ionizes into hydrogen ion and your hydroxyl ion. Okay, in solution, now we'll go to this later on. What happens is your carboxyl group will become is acidic, right? So now donates it now donates your hydrogen ion. Okay, it now donates your hydrogen ion. So your COOH donates your hydrogen ion, so it becomes your carboxylate. Let's take note of the semantics. Okay, this is your carboxyl group. When we say of carboxyl group, it is COOH. When we say of carboxylate, it is already ionized. Okay, so it's COO negative. Sometimes you will see this process as ionization. Sometimes you'll see this process as dissociation. No, it might be confusing, but for all intents and purposes, no, for discussions like this, it's best that let's use this a common term. No, deprotonated. Deprotonated. In other words, you remove a proton. What is basically a proton? A proton is a hydrogen ion. Okay, so the acidic part of your amino acid is your carboxyl group. And what is a Bronsted base? A Bronsted base, again, is something that can accept a hydrogen ion or a proton. Okay, in your amino acid, what will act as your Bronsted base is your amino group. Your amino group can now accept its hydrogen ion or proton. It will now become your protonated ammonium ion, no? NH3, sorry, no, that's NH3. Or okay, balik that. NH3 positive, no? NH3 positive, that is protonated. So please let's get used to this. Okay, ionization of carboxyl to carboxylate is deprotonation or dissociation or ionization. No, but to to get used to it, no, for me personally, I use deprotonation. Okay, so clear in my mind that I know that hydrogen ion is being removed. Okay, protonation on the other hand is when you add a proton. When you add a proton, it becomes your ammonium ion. Okay, so let's now look into this. So let's go to the meat of the matter, titration of amino acids. Well, we know very well that amino acids are ampholytes. So in the its truest meaning of the word, it is an ampholyte. It can act as an acid. It can act as a base. So in other words, you can titrate that against an acid or against a base. Okay. However, no, to really understand this, most books will really start. No, most discussions will start the titration from the lowest pH. From pH 0 or pH 1. When you have very, very low pH, you know what pH means, right? pH is the negative log of your hydrogen ion concentration. So if your hydrogen ion concentration is very, very high, your pH is very, very low. Okay? So pKa, we will go to that later on. So if your pH is high, most probably it will be below the pKa. The pKa is the dissociation constant, the pH of the dissociation constant of that particular functional group. Now we'll go to that later on. So as I mentioned a while back, if it is protonated, it is still carrying its hydrogen ion. So if your pH is very, very low, now I'm just setting the ground, okay, so that when we go to titration later on, it will be easier to understand. So if you have an abundance, a preponderance of your hydrogen ion concentration, what does it mean? Your carboxyl group will be protonated. In other words, it will be undissociated or unionized. Okay, it is carboxyl group, COOH. Your amino group, on the other hand, is protonated. COOH is acidic, right? That is your acidic. It donates hydrogen. Okay. Your amino group is what? Your amino group is basic, so it accepts the hydrogen ion. In the milieu wherein your hydrogen ion is very, very high or your pH is low, Okay, most probably, no, it will be lower than the pKa of the functional groups because it's very, very low. No, so both moieties will be protonated. The carboxyl group is undissociated. The amino group is protonated. Okay, the carboxyl group is not deprotonated, or both are protonated. No, to put it simply. So when you titrate, okay, when you titrate, what is happening? No, your hydrogen ion is decreasing, right? Because when you add sodium hydroxide, no, this when you add sodium hydroxide, what happens? Sodium hydroxide will react with hydrogen ion to form water. So in other words, you are decreasing your hydrogen ion. Okay, you're decreasing your hydrogen ion concentration. When you decrease your hydrogen ion concentration, what happens? Your pH increases, right? When your pH increases, so later on when we see the graph, it will be going upwards. But to train ourselves, okay, when you add sodium hydroxide, no, this is negative. For me, no, what I remember is I don't anymore deal with hydrogen ion concentration, but with your hydroxide concentration because they have different charges. Okay, so this will make it easier later on. So at higher pH, we expect the negative moiety to predominate. So in this case, your pH is getting higher because your hydrogen ion concentration is getting lower, right? Or indirectly your hydroxide ion is getting higher. What happens? Now your pH will surpass your pKa. Okay, your pH will surpass your pKa. So in the absence or in the paucity of your hydrogen ion concentration, what happens to your COOH? Because it is acidic, no, it is generous, it is acidic, it will give off its hydrogen ion. So it will be deprotonated, or some books ionized or dissociated. But for simplicity's sake, no, let's just be of one mind. Okay, let's just use protonated or deprotonated. So what happens to your COOH? Your COOH will now be, your carboxyl group will now be carboxylate. Okay, will now be carboxylate. Your amino group, which is basic, no, basic, it grabs its hydrogen ion, but your hydrogen ion concentration is scarce. No, you have a paucity, you have an absence, you have starvation of hydrogen ion. What happens? Although it is basic, it does not have any choice but to let go. Okay, sometimes it's hard to let go, no? But your amino group, just like most of us, we have to let go. Okay, we have to let go. So for neutral amino acids, we will see this later on. At very, very low pH, no, it will be cationic. Cationic, no? Makes sense, right? Because you have a lot of hydrogen ion concentration is very, very high, right? The pH is very, very low. Your amino acid will most probably be cationic. Okay, this is a usual question in the exams. If it is cationic, where will it go? To the cathode or to the anode? We know that this is positively charged, right? So it will go to the negatively charged pole. It's the negatively charged pole cationic or anionic. Sometimes we get confused, right? So is it the cathode or the anode? Sorry. Is the positive ion, the cation, migrate to the cathode or to the anode? No one is commenting, no. But for me, when I was in school, I really get confused, no. But a professor of mine told me, uh, for you to remember a lot easier, just remember that the pole is named after the ion. The pole is named after the ion. So if the ion is positive, no, it is a cation, it is cationic, it will migrate to the cathode, which is negatively charged. Okay, so simple as that. Okay, all your doubts will be erased. Hindi na makakalimutan, no? It's not easy to forget anymore. Okay? So your positive ion, your cation will migrate to the cathode, which is negatively charged. Okay, thank you for the comment. Ralph, okay. Thank you very much. However, no, at high pH, okay, thank you, Ralph Lauren. At high pH, we expect your hydrogen ion concentration to be low, no, but just remember your hydroxide ion will be high. Your hydroxide ion will be high. It is negatively charged. So if the pH is above the pKa, no, of that functional group, okay, when we say of pKa, that's the functional group, not of the entire amino acid. It's a functional group. Okay, so if the pH is more than the pKa, so what happens now? Relatively speaking, you have a paucity or scarcity of your hydrogen ion. Your carboxyl group, right, will now be deprotonated to your carboxylate. and your amino group, although it's basic, no, it has to grab the hydrogen ion, it's an acceptor, it has to let go. So it becomes anionic. If it is an anion, if it is an anion, it's negatively charged, it will now go to the anode. Okay, it will now go to the anode, which is positively charged. No, so I hope I cleared things up. So you can take a screenshot. No, this is really very helpful. Okay, so that when we titrate, later on, especially the trifunctional amino acids, no, trifunctional amino acids, if the pH is very low, no, below your pKa, you have an abundance, a preponderance of your hydrogen ion concentration. What happens? Your acidic group, your COOH, although it's acidic, no, it's generous, it will give. It will not have to give, no, because you have a lot of hydrogen ions around, no, okay, in the environment. And your amino much more, no, your amino group, since it's basic, no, it's actually it's selfish, no, it will now hold on, no, it will be happy, no, with its hydrogen ion. So this will be cationic, it will migrate to your cathode. On the other hand, no, on the other hand, when you add your hydroxide ion, what happens? No, your hydrogen ions will react with your hydroxide ions to form water. No, your hydrogen ion concentration decreases, and your pH will now be above your pKa. Your moiety, your functional groups will be deprotonated. No, your carboxyl group will be your carboxyl group will now be carboxylate, COO negative, and your ammonium, okay, although it's basic, will have to let go its hydrogen ion. So the overall charge, when you put the two functional groups together, now if you only have two functional groups, it is anionic. Okay, it is anionic. It will now migrate to your anode. So for your neutral amino acids, let's titrate. Okay, let's titrate. So you saw this. What is this? No, this is one of the simplest amino acid. No, it's aliphatic. It's non-polar. Okay, it's neutral, non-polar. It is non-essential. This is your alanine. No, alanine is usually the poster boy of your neutral amino acids in titration. Okay, so I just put this here to remind us. No, for virtual milestone, okay, to remind us as a benchmark. So when we start with let's always start with the most acidic, okay. If the pH is very low, you have an abundance of your hydrogen ion concentration. What do you expect? Your alpha carboxyl will be protonated, okay? Your amino group will be protonated. So both will be protonated. This is undissociated, unionized, or protonated, no? Just to be simple, your amino group is protonated. So these are the two moieties. If you're going to look at the charge, okay, so this is zero. Your carboxyl group is zero, okay? It is zero, it's neutral, but your amino group, ammonium ion, is +1. So the charge here is +1. It is cationic. It now migrate to the cathode. Okay, so let's titrate. What happens now? If we add on more sodium hydroxide, if we add on more hydroxide, what happens? We are decreasing the hydrogen ion concentration. If we decrease the hydrogen ion concentration, okay, you'll come to a point. Now we'll be discussing pKa later on. You'll become to a point that the hydrogen ion concentration becomes lower than your pKa. So what happens now? No, your something has to give. No, your hydrogen ion concentration is falling. If I'm going to ask you, and I'm asking you now, which of the following is more acidic, the carboxyl or the amino group? Which is more acidic? We know very well that your carboxyl group is acidic, right? Is acidic. So which will give its hydrogen ion first, the carboxyl or the amino group? Of course, no, of course. What will give first will be your carboxyl group. Okay, your carboxyl group, because it's acidic, right? It's acidic. Wait, I'll change the banner. Okay, so if you're finding value, okay, if you're finding value to in this video, no, and of some of your classmates who'll be benefited from this, kindly share this video, and if you might consider subscribing to my channel as well. Okay, anyway. Okay, anyway, so what do we have here? So the carboxyl group deprotonated. Okay, the carboxyl group deprotonated. The ammonium does not have, okay, does not have to deprotonate yet because the pH is not yet that high. Okay, the pH is not yet that high. It hasn't reached the pKa of your amino group. So what are the moieties now? We have your carboxylate and you have your ammonium ion. So this is -1. This is your +1. +1 minus 1 is 0. Okay, so this is your sweeter ionic now. Sweeter ionic came from a German word, okay, meaning a doubly charged molecule, no, with a zero charge, with a net neutral. No, it's neutral. It's dipolar. No, it's dipolar. It has two charges, but they cancel each other out. Okay, so it will not migrate. It will stay put. It will stay put. Okay, so you keep on adding more hydroxide. You keep on adding more hydroxide. So what happens now? No, the pH will be higher than the pK2. Okay, of your amino group. Of your amino group. By the way, no, if the pKa, we'll go to the pKa values later on. The lower the pKa value, the more acidic the moiety is. The lower the pKa value, the more acidic it is. Okay. So in this case, your pK1 will be referring to your carboxyl group. So in this case, your pK2 we're now referring to your ammonium ion or your amino group. So if you keep on adding hydroxide and you keep on removing your hydrogen ion, the pH goes up, right? What happens now? Your ammonium ion will have no choice but to let go. Sometimes you have to let go. It has to let go. So, okay, so sorry, that is your sweeter ion, no? Sweeter ion, zero charge. So the next step is what? No, you keep on adding your hydroxide. So what happens now? Your ammonium ion will deprotonate. No, your ammonium ion will now deprotonate. So our moieties now, you have your carboxylate with a charge of -1 and your amino group with a neutral charge with a zero charge. Okay, so the net charge is -1. The net charge is -1. It is anionic. It is the anion. So it will now migrate to the anode, which is the positively charged pole. So for 13 of the 20 amino acids, now later on I have a classification. It's important. Okay, it's important that we wait. Okay, carboxyl. Okay, so it's important that we know the different amino acids. I know you have 20, right? And doc, there's so many. Later on, I'll give you a simple way, no, a simpler way to remember the classification. So 13 of the 20 amino acids are difunctional. No, they have only two functional groups, your carboxyl and your amino group. So if you have only two functional groups, you have only three ionic species. Okay, you have only three ionic species. So in this case, that is your cation. Cation, we know very well at low pH, no, you have a lot of hydrogen ion concentration. Okay, your cation will be at very, very low pH. When you titrate with your hydroxide, which is negative, no, when you go no to when you keep on adding your hydroxide, you keep on removing your hydrogen ion concentration, the pH increases, right? It becomes now your anion. But before going to that, you have a stopover. No, there will come a time that your species will be your carboxyl group will be carboxylate, your amino group will be protonated. Protonated. You have negative and positively. It's doubly charged, no, but the overall charge is 0. Okay, this is your sweeter ion. So if your cation, that will migrate to your cathode, your sweeter ion that will stay put, and your anion that will migrate to the anode. So in this case, no, this is a simpler form, no. So you have three forms. This is your cation. This is your anion near your neutral pH, no, pH 6, pH 7. Okay, your carboxyl will be negative. Your amino will be positive. So you know that the pH, no, you have this formula, no, pK of the functional group plus log of your what, no. This is your conjugate base of the acid over the acid, no. So in this case, 2/1. What happens is when you reach a point wherein you have equal concentration of your cation and sweeter ion, you have equal concentration. So for example, this one and this is 1, the log of 1 is 0. What happens now? Your pKa, what is your pH? Now the pH becomes your pKa. So your pKa is the point in the titration curve wherein you have 50% of each of the ionic species on either side. On either side. So, if you have a situation wherein the pH is exactly congruent, not exactly coincidental to your pKa, it only means one thing. Your ionic species on both sides, for example, your cation and your sweeter ion will be equal. 50-50%, okay, will be equal. Will be equal. No? So you have 50% of this, you have 50% of this. On the other hand, no, if you keep on titrating, so this is your sweeter ion and this is your anion. If both of the species exist in the same amount, okay, in the same amount, that is the pKa of your amino group. That is the pKa of your amino group. So going back, now revisiting. So this is your very, very low pH. No, this is your high pH, high hydrogen ion concentration, cation, sweeter ionic, anionic. Okay, so if the pH, if your concentration of your cation is equal to the concentration of your sweeter ion, what happens? Okay, they cancel out. The pH becomes or equal to your pKa. It only means one thing. You have your cationic form and your sweeter ionic form are equal. Okay, they're equal to each other. If they're equal to each other, the pH is your pK. Okay, the pH is equal to your pK. And we know that your amino acids conserve, although it's not that significantly, okay, in a minor way. Your amino acids like histidine can serve as important components of your buffering systems. Okay, if you can see, you have areas. Okay, you have where in your titration curve plateaus. Okay, you have a plateauing of the curve. You have a plateauing of the curve, and this will coincide with your pKa values. So if there's a question in the exam, now which of the which of the following points has the greatest buffering capacity, it is the region of your pKa. Okay, it's the region of your pKa or the pH that will coincide to your pKa values. You can see you have a plateauing. Okay, you have a plateauing. Okay, so this your sweeter ion on the other hand, no sweeter ion. Um, what happens to the pH? No, if your pH is equal to the point wherein you have the greatest concentration of your isoelectric, no, your sweeter ionic, that will now correspond to your isoelectric point. Okay, isoelectric point is the pH wherein your species will be sweeter ion. No, in other words, it does not have any charge. It does not have any charge. And for neutral amino acids, it's simple. It's just the average of your two pKa values, the average of your two pK values, because you don't have any choice, right? You have only two pK values, so you have no problem with that. The problem comes when you are dealing with trifunctional amino acids. What do we mean by trifunctional amino acids? All amino acids will have at least two functional groups. Okay, you have your carboxyl group and your amino group, but 7 of the 20 will have a third functional group. We'll have a third functional group. Okay, so let's just go through this very, very quickly. Anyway, this is really very helpful. You have 20 amino acids, and sometimes you might have questions in the exams. Which of the following amino acid is essential, is polar, etc.? No, is essential, it's polar, will not ionize, etc. No, so it's really confusing. It's really confusing, no? And sometimes students will use their mnemonics. Problem with mnemonics is sometimes they're weird, right? Sometimes they're weird, they're out of this world, and sometimes you know the letters, but you don't know where they stand for, right? For example, if the mnemonic comes for a letter T, which of the amino acids starts with the letter T? You have three amino acids that starts with the letter T, and I think you have three that starts with the letter A, etc. No, so don't mind the mnemonics. It's essential amino acids. There's a mnemonic aside from that. But an easier way is what? No, you have 20. Your acidic have 4. Okay, we have to go through this, and students, no, I think it's prudent. No, I don't only recommend, but I highly encourage that you remember the 7. Okay, you remember the 7. There's only 7. Eh. We have 4 here, no, but they're useful as well. So you have four acidic amino acids. It's a little controversial in some books, no, but I when I looked around, no more books will state that you have four acidic amino acids. The strongest is your aspartic. We will see more about aspartic later on. It says it is the strongest acidic aspartic. It's the strongest acidic amino acid. And we will see later on their third functional group. It's also prudent. Huh? You write it down. You should remember the third functional group. The third functional group of your aspartic acid is your beta carboxyl. Okay, the second strongest acidic amino acid is your glutamic acid with its gamma carboxyl. Then what are the two weak amino acid acidic amino acids? What are the two weakly acidic amino acids? Your cysteine. Okay, please do remember that the third functional group, cysteine, is acidic. No, your sulfhydryl group, it ionizes. Okay, your sulfhydryl group, your SH ionizes. Sulfur is highly electronegative atom. An electronegative atom is an atom that has a high attraction to the shared electrons. So hydrogen can be given off. So this is your sulfhydryl group. We'll see that later on. And tyrosine. Okay, sometimes tyrosine can be classified as hydroxylated. Yes, no, because you have a hydroxyl group. Okay, but it is an acidic amino acid. It's weakly acidic amino acid. No, your pi electrons can delocalize, including the electrons of oxygen. Hydrogen can be given off. So please remember this four. For your basic, you have only three. No, I have a mnemonic for this. No, you have your weakest base. That is your histidine. That is your histidine. The third functional group of histidine, we'll see later on, is your imidazole. Imidazole. Please remember the third functional group because they can ionize, they can participate, no, in the titration. The next is your most basic. Okay, the most basic is arginine with its guanidinium. Okay, guanidinium functional group, guanidinium. Okay, and last is your lysine in between. Okay, histidine is the weakest, arginine is the strongest base, then your lysine. Now we'll see lysine, we will titrate lysine. The third functional group of lysine is your epsilon amino. So if I were you, okay, just remember the seven: four acidic and three basic. And these are the amino acids that will become charged. Okay, they ionized. Then the 13, they are neutral. But it does not end there, no? When you're neutral, it does not mean that you're nonpolar. But you can, no, you may not just remember, you may not remember this, no, you just remember the seven, it's okay. But the question is, which of the following amino acid does not ionize but can participate in hydrogen bond formation? Okay. So I think it's prudent. Let's go into the polar very, very quickly. You have only four polar amino acids. Okay. Four polar neutral amino acids. And they have a rhyme and reason for being such. Okay. So basic hal, I forget. No. So mnemonic hal, no. You know the movie. Okay. Shallow hal. Forget Minute Pulse and Jack Black. Okay. I hope you remember that. Okay. So basic hal. Basic hal. For the polar neutral amino acids, you have only four. Your two hydroxylated. No, serine is hydroxylated, and your threonine, they're hydroxylated. Hydroxylated, you have your OH group. Okay, oxygen is what? Oxygen is highly electronegative, so hydrogen can participate in hydrogen bond formation. Okay, so for both serine and threonine, no, we don't have time to look into the structure. You just go back. Okay, then oxygen is highly electronegative. Aside from that, no, your nitrogen is also highly electronegative. So your aspartic acid, your third functional group, like your beta carboxyl or for aspartic acid, and your gamma carboxyl for glutamic acid, they can be amidated. Okay, they can be amidated. Yung C double bond O NH2. So your asparagine and your glutamine are amides. Okay, are amides. These four, okay, these four. Please remember na lang these four. Okay, your two hydroxylated and two amidated amino acids, they are polar neutral. They are polar neutral. So if you have a question, which of the following amino acids are you given for? Then the question is, can be found or will be located uh, within, no? Can be located within. In other words, if you have a globular protein, these amino acids are located inside, no? Because the inside, that's your hydrophobic region. The outside, no, the amino acids that are located outside in the globular protein should be what? Hydrophilic. And what are your hydrophilic amino acids? These 11, okay? These 11 are hydrophilic. So what can be found within, no? These are your neutral, non-polar, hydrophobic. So they're not included here. So don't remember them. So if they're not here, they are neutral, they are non-polar. Okay, so this, no, you may not remember. Just remember, it's easier just to remember this four, this three, and this four. No, your hydroxylated and your amidated, then you're done, right? You can answer. If the question will ask which of the following amino acids are located outside exposed to water, so you now have to look into the amino acids that can ionize or the amino acids that can form hydrogen bonds. Okay, so this is the problem. So again, no, your trifunctional amino acids, they are trifunctional for the reason that all of them, no, all amino acids will have your alpha carboxyl, all amino acids will have your alpha amino group, right? But God gave us challenges in life, right? So you have a complication. No, life is complicated. It's complicated, okay, just like relationships, because their side group or their R group can ionize. Okay, their R group can ionize. So I mentioned this a while back. In almost all the exams, no, they ask the functional group. So for aspartate, this is your beta carboxyl. This is the most acidic. For glutamic acid, it is your gamma carboxyl, no? GG, no? Same, ano, gamma carboxyl, right? They are acidic, and cysteine, you have your sulfhydryl group, no? Your sulfhydryl group, and your tyrosine, you have your phenyl hydroxyl group. So 1, 2, 3, 4. You have your four acidic. Their third functional group can ionize. In other words, they can what? They can exchange hydrogen ion, either give it off, give it away, or keep it, no? Or keep it, no? They're acidic. Eh. Aside from that, you have your three basic, no? Basic Hal. Okay, so histidine, pay particular attention to histidine. No? The pKa of your imidazole group. Please remember the third functional group. No? This is your imidazole group. Your imidazole group, the pKa of this is around 6. So histidine, no, we'll see this later on. Okay, hopefully we're still around. Now your imidazole is 6. Okay, so 6 is near 7. No? It's near your physiologic pH. So histidine plays a very important role in your buffer, no, in your buffers. Okay, so your histidine, your functional group is imidazole. For your lysine is you have your beta. So this is beta, gamma, delta, epsilon. Okay, so your third functional group for lysine is your epsilon amino group. Then for arginine, it's your guanidinium. Guanidinium. So if we're going to look at this, sige, let's go to the next. Okay, if we're going to look at this at low pH, again, I cannot overemphasize the fact. Okay, at low pH, the hydrogen ion concentration is very, very, very high. Your pH is very, very, very low. In most of the time, most probably it will be lower your pKa. So what do we expect? If it is an acid, your carboxyl group, no, you have 1, 2, 1, 2. Your carboxyl group will be will not is undissociated. No, it will remain as a carboxyl group. Because they don't have to give off its hydrogen ion. No, they don't have to give off hydrogen ion because you have a lot of your hydrogen ion. And the same way, no, your sulfhydryl group will stay as sulfhydryl. Your phenyl hydroxyl, no, will remain as phenyl hydroxyl. Those are for the acidic. But look at here. Look at the basic. Look at the bases. For your lysine, the amino group is protonated. No, we know very well that your amino group is basic. It accepts a proton, and the pH is low. The hydrogen ion concentration is high. It means that this condition is perfect. I don't have to give off. I'll keep the hydrogen ion. So look at the epsilon. It's positive. Then the guanidinium, then just look at the structure. Your guanidinium, you have a positive nitrogen as well. Okay, you have positive nitrogen as well. Same with histidine. No, sometimes this transfers because you have resonant forms for your imidazole group. This is for your This is for your low pH, high hydrogen ion concentration, wherein the pH is most probably below the pKa. Let's look at the other side of the coin. Okay, the other side of the spectrum. What happens if your pH is high? Okay, it's high. When your pH is high, what's the condition again? Your hydrogen ion concentration is low, or your hydroxide ion concentration is high. The pH is high, so you have a starvation, or you have a paucity. You have a scarcity of your hydrogen ion, right? You have a scarcity of your hydrogen ion. So what happens now? Most probably the pH will surpass the pKa. No, the pH will surpass the pKa. Your acidic groups. Look, your carboxyl groups and your sulfhydryl and your phenolic your phenyl hydroxyl groups, because they're acidic and the pH is higher than the pKa. Now you have a relative scarcity of hydrogen ion. They have to deprotonate, or they have to dissociate. So your carboxyl will now become carboxylate. Your sulfhydryl will become S negative. You can see the charges, right? Carboxyl is always negative. Your sulfhydryl is negative. No, then you have your hydroxyl ion. Okay. So for the acids, the carboxyl group will become deprotonated, will become negative. On the other hand, for basic, right, for the basic amino groups, if you have hydrogen ion, they will keep it, right? Because they accept hydrogen ions, right? And they have a charge of positive. However, at high pH, with relative scarcity of your hydrogen ion, they have to let go. So in this case, look at this. The amino group will be unprotonated, will be deprotonated. So here, no, as compared to this, you don't have any positive charge. Your NH2, your amino group is neutral. Same with your epsilon amino for lysine. Epsilon amino for lysine, it is neutral. For the guanidinium, it does not have any charge at all. Okay, so titration of your neutral amino acid is complicated enough, right? But you have a third functional group. So it complicates matters. But we'll see. No, let's look at your acidic amino acid, our poster boy, the usual representative of the four acidic amino acids that they use is your aspartic acid. No, aspartic acid again is what? No, it's a trifunctional amino acid. It has its alpha. No, this is again your alpha carbon is your carbon that is directly attached to your carboxyl carbon. This is carbon 1, your alpha carbon is carbon 2. Okay? So this is your alpha carboxyl group. This is your alpha amino group. Then the third functional group of your aspartic acid is your beta carboxyl. Okay? Beta carboxyl. Again, what do we mean by pK? pK is the pH wherein you have 50% of the carboxyl group and 50% of the carboxylate. So in other words, if the pH is equal to 1.9, what happens? You have 50% of your COOH and you have 50% of your COO negative. Okay? Then looks, what happens? Now what is the next functional group that has a low pK? It is of course your acidic group. Again, no, if the pK value is very very low, it's most probably acidic. It's acidic. No, it can easily give your hydrogen ion. Your beta carboxyl, the pKa is around 3.7, right? So at 3.7, you have 50% of your carboxyl, you have 50% of the carboxylate. If you're asked carb which of the two carboxyl groups is more acidic, alpha carboxyl is always acidic, okay, because it has the lowest pKa. If you're going to look at glutamic acid, now the pKa of your gamma carboxyl group is around 4 point something, no, higher. The pKa is higher, it means it is less acidic than your beta carboxyl. So the most acidic is your alpha carboxyl, followed by your beta carboxyl, followed by your gamma carboxyl. Then the least acidic, because it is most basic, it's your alpha amino. So if we're going to titrate, what is the sequence now? If we're going to titrate, which is the sequence now? Which will be the first group that will easily give off its hydrogen ion? Is the first group that can easily protonate? The most basic, the most acidic, the most acidic. So the first to deprotonate will be your alpha carboxyl. The next to protonate will be your beta carboxyl, and the last to deprotonate to give off its hydrogen ion will be your alpha amino. It follows because your alpha amino is basic, right? It's in the business of accepting your hydrogen ion or your proton. So I'll reiterate, no, the lower the pKa, the more acidic is the functional group. The lower the pKa, it's more acidic. The higher the pKa, it is less acidic, or it's more basic. It's more basic. So again, okay, so You just stay put. Don't go into convulsion. Look, this no, no, it's easy. No, it makes sense. Actually, it really makes sense. So let's orient ourselves. So this is your pH zero. Sorry, no, this pH zero. This is 14. You add your hydroxide ion. So in other words, when you go to the right, what happens? Your hydrogen ion concentration decreases. No, your functional groups will have to deprotonate. Your functional groups will have to deprotonate in their proper sequence. Okay, in their proper sequence. So again, no, at high hydrogen ion concentration, please remember, no, your COOH, the acidic part, will be what protonated, same with your amino group. But if your pH, if you have a lot of your hydroxide ion, okay, your hydrogen ion concentration is low, your carboxyl group will have to deprotonate, and your amino group will be deprotonated as well, giving rise to their respective charges. So in this case, if we're going to look at this at the most acidic, okay, at the most acidic, what is the? I apologize, it's quite small. No, I hope you can still see. Okay, this is your aspartic acid. This is your alpha carboxyl, right? I hope no you can see this is your alpha carboxyl. This is your alpha amino. So this is your alpha carbon. This is your beta carbon. This is your beta carboxyl. Okay, for your own sake, please remember the third functional groups. No, it's a favorite question. Okay, favorite question of your professors. Okay, so if we're going to look at this, your carboxyl group are not deprotonated, right? So it's undissociated, it's unionized, and your amino group is what? Your amino group is protonated because your pH is very, very low. Your hydrogen ion concentration is high. No one has to give. No need there. Why will I give? We have a lot of hydrogen ions around, right? So if we're going to look at this, what are the functional groups? Your alpha carboxyl is as undissociated. Okay, your beta carboxyl is undissociated. Your amino group is protonated. So the charge is what? The charge is plus one. Huh? The charge is plus one. So it will go to your cathode. It is cation. So one clue that I give to students, if they don't want to think anymore, no, they just want to raise their hands and give up. If you have a pH is low, don't choose the negative. Don't choose the species that is negatively charged. No, most probably it will be positively charged. That will narrow down your choices. Okay, that will narrow down your choices. At least, no, if you're going to guess, no, you have a greater chance of getting it right. So, so what happens now? No, we're titrating. We're adding more hydroxide ions. Look at this. If I'm going to ask you which of the three functional groups will give first, who will give first? Your alpha carboxyl, your beta carboxyl, or your alpha amino? I cannot hear. Okay, anyway, we're not in a small group discussion. So please remember, the one that is the most acidic will deprotonate first. The one that is the most acidic. Okay. If we're going to remember the pH, the pKa, um, at the least, please remember the pKa values of your alpha carboxyl. Alpha carboxyl is around 2. Okay, it's the most. I think it's the most acidic. No, it's 2. No, it's the most acidic functional group, your alpha carboxyl. The beta carboxyl is around 3.5, if I remember, no, around 3 something. Then your alpha amino is 9. But alpha amino group is not the most basic. We will see later on. It's not the most basic. It's basic, but you have functional groups that are more basic than your alpha amino. So from here, now knowing the pKa values, the one that will donate first will be your alpha carboxyl, right? Do you see? The alpha carboxyl the alpha carboxyl gave off its hydrogen ion, so this becomes carboxylate. So our functional groups now is your alpha carboxyl is deprotonated, your beta carboxyl is still protonated, your alpha amino is still protonated. So if you're going to look at this, the charges cancel out, right? This does not participate, it is neutral. So what do we have here? Now what do we have here? The charge here is what? No, the charge here is zero. What do you call that? what do you call that species wherein you have two charges, but the overall charge is neutral? What do you call that? That is your isoelectric. Okay, that is your isoelectric point. That is your isoelectric point. So if it is subjected to electrophoresis, it will stay put because it does not have any charge. It does not have any preference if going to the cathode or going to the anode. So if we continue on titrating, if we add more if we add more hydroxide ions, which do you think will give off its hydrogen ion? The alpha carboxyl or the alpha amino? Of course, what will give off the carboxyl, no, by virtue of its definition, is the more acidic. Your carboxyl group is an acidic group. No? The pKa of your beta carboxyl is around 3 something. This is around 9. Okay, sweeter ion, right? No, that's your sweeter ion. That's your sweeter ion. But we're titrating now. No, we're adding more hydroxide. We're removing your hydrogen ion, which will participate, which will deprotonate, which will give first the beta carboxyl or the alpha amino. Of course, the more acidic. The more acidic. It is your alpha carboxyl that will give first before your alpha amino. Your alpha amino is the last because it's the least acidic, it is the most basic. So our moiety now is you have two carboxylates. Right, John. Okay, like Cantaroni. Okay. So thank you very much. Thank you very much for participating. Or shout out. Shout out to Ralph Lauren Casser, John Beltran, Ralph Kentaroni Oyama. Okay, so thank you very much for participating. So from here, we can see that it is your beta carboxyl now that will deprotonate. So you can see the sequence, right? Do you see the sequence? When giving off your hydrogen ion or your proton, it's the most acidic first. Okay, most acidic, then eventually going to the least acidic, the less basic, then the more basic. Okay, so that's the sequence. So our moieties now is your alpha carboxyl is negative, it's carboxylate. Your beta carboxyl is negative, it's carboxylate. Then your alpha amino is still protonated, no, because the pH is still not high enough to reach the pKa of your alpha amino. So in this case, you have two negative charges. You have one plus charge that is due to your alpha amino. The charge here is -1. Okay, the charge there is -1. Then you keep on adding, okay? Keep on adding your sodium hydroxide. It comes to a point that your hydrogen ion concentration is really very, very scarce. Okay, it's very low. It's very low. Your pH is very high. Your pH is very high. You have surpassed your pK values for your alpha amino. So for example, the pH is more than 9 already. So what happens? No one can give anymore. The amino group, although it's basic, will have no choice but to let go. But to let go. But to let go. So what you have here now is what? No, you have two negative charges plus your neutral. So the charge here is -2. Is -2. Okay, so if we're going to look at this, no, to connect things, you know very well that aspartic acid is an acid, right? Why is it an acid? Because it has an additional carboxyl group. You know very well that carboxyl group is negative, right? When once it's ionized, so your carboxyl group, alpha carboxyl can be negative, your beta carboxyl can be negative. So you can surmise that your aspartic acid can have a charge of -2 because we know that your trifunctional amino acid, sometimes we get confused. We get confused. The one that would be the -2, is it aspartic acid or is it lysine? Yes, it's very easy. It's very easy to be confused, right? It's very easy to interchange. Just remember this, students. Just remember this. Aspartic acid is acidic because you have an additional carboxyl group. Your carboxyl group can protonate. No, your carboxyl group can protonate. So potentially, if you have two carboxyl groups, they can deprotonate, no, they can dissociate or ionize, and they become carboxylate. So potentially, aspartic acid, by virtue of its two carboxyl groups, can have a charge of -2. So as simple as that. So that you might not confuse, kasi sometimes we memorize. If you memorize, that's rote, no, that's passive learning. But active learning, if you just connect things, na connect it to the material. Your aspartic acid has two carboxyl groups. Two carboxyl groups hanggang -2. That can reach -2. Same with lysine later on, right? So look at this. The 13 of the 20 amino acids have three ionic species, right? But your trifunctional amino acids, because they have three functional groups, they have three pKa values, you have four ionic species. In this case, you have two anionic forms, you have sweeter ion, and you have your cation. And you know very well, if you know the charge of the amino acid, you know to which pole it will migrate to. So, uh, looking now at your pKa and your isoelectric pH, from here you can see areas of buffering, right? And you know very well, again, how do we define pK values? pK values is the pH wherein you have 50% of both species on either side. So at this point, no, for example, this is the pKa value of your alpha amino. Let's just presume, no, that this is 2 and the pH is at 2. You can very well say that you have 50% of this ionic species, the plus 1, and 50% of the sweeter ion. Okay? And it is this point wherein you have the greatest buffering capacity. No, you have your greatest buffering capacity because you can plateau. They are useful as buffers. No, what are buffers? No, they can cushion changes in the pH if you add an acid or a base. No, because of the relationship, because of the acid and the conjugate base, and vice versa. On the other hand, what is the pH wherein you have your sweeter ion? No, the pH wherein your sweeter ionic form exists is your isoelectric pH. No, your isoelectric pH. For your neutral amino acids, you don't have any problem, right? Because you have only two pKa values. But this is where the problem lies. Sometimes students get confused. Is it pK1 plus pK2 divided by 2, or is it pK2 plus pK3? I'll tell you a simple way to remember. For acidic amino acids, it's the first two. Again, no, I hope some books kasi PKR, no, that's confusing eh. It's best, no, it's better if your professors will use PK1, PK2, PK3 because they are arranged in the increasing pKa values. So pK1 is lower than pK2, pK2 is lower than pK3. For acidic amino acids, please remember it is the Pi, or the isoelectric pH, is just the average of the two most acidic. Yan na, acidic. Two most acidic functional groups. So in this case, it's your alpha carboxyl and your beta carboxyl. So for you to remember, if you're asked to compute the isoelectric pH of an acidic amino acid, just get the two lowest pKa values. Okay, the two lowest pKa values, no, regardless of their label, because the two lowest pKa values are the two most acidic pKa functional groups. You get the average of the isoelectric pH, or the Pi of your acidic trifunctional amino acid, is the average of the two most acidic functional groups. And that makes sense, right? That makes sense, right? Okay. So let's now go to your basic amino acids. How many basic amino acids? If we remember, we have only three, right? We have three basic hull. You have histidine, you have arginine, we have lysine. Histidine is a little complicated. Arginine with its guanidinium group is a little complicated. So most books will use the simplest basic amino acid, that is your lysine. Okay, this is your lysine. So I am sure you can recognize. No, you can recognize the functional groups. This is your alpha carbon. So this is your alpha carboxyl. This is your alpha amino and your alpha, beta, gamma, delta, epsilon. So the third functional group for lysine is your epsilon amino. Your third functional group for lysine is your epsilon amino. If we're going to titrate lysine, what is the sequence? Doc, I know that. I know that. The sequence is you get the alpha carboxyl, then the third functional group, then your alpha amino. No, you look into the pKa value. Okay, you look into the pKa value because we go from lowest to highest number. We go from lowest to highest number. Alpha carboxyl is around 2. So in this case, for lysine specifically, it's 2.2. And look at this. In aspartic acid, right? In aspartic acid, your alpha amino pKa is higher than your third functional group. But look here, look in lysine, the alpha amino is not the most basic. Huh? It's not the most basic. The pKa is 9. It's pK2, no? pK2. But look, your epsilon amino has a higher pK value than your alpha amino. So the sequence of deprotonation is what? No, so deprotonation first is your alpha carboxyl. Okay, so again, the pKa, the lower the pKa, the more acidic, the higher the pKa, the less acidic. But if we're going to titrate lysine, what is the sequence? What is the sequence of deprotonation? So the first to protonate will be the most acidic, right? So it's your alpha carboxyl. It's your alpha carboxyl. Which will deprotonate next? Will it be your alpha amino or your epsilon amino? Which will deprotonate first? Which will give off its hydrogen ion? The alpha amino or the epsilon amino? The one with the lower pK2. In other words, the one that is more acidic or the one that is less basic, right? I know it's confusing. I know it's confusing. Right, no, right. So John and Jacobs, no, so it's your alpha amino, right? It's your alpha amino because it has the lower pK value. So it's your pK, it's your alpha amino, and what happens, no? From positive, it becomes neutral, right? From positive, it becomes neutral. Then eventually, it will be your epsilon amino. So we can see from here that your epsilon amino is really a very basic, huh? It hangs on, no? It will hang on to its hydrogen ion until the end, no? Until it has to really let go. Okay, has to really let go. So let's titrate. Let's titrate. This is your lysine. I hope you can see. No, this is your lysine at very low pH. Very low pH. We can see that your alpha carboxyl is protonated, your alpha amino is protonated, your epsilon amino is protonated. So this will be our moieties. Your carboxyl group is carboxyl, it's protonated with no charge. Your alpha amino is still protonated plus 1, and your epsilon amino is protonated. Okay, so plus 1. So the total of plus 2. Again, to help you remember, which will have amino acid that is potentially can have a charge of plus 2. Can have a charge of plus 2. Is it aspartic acid or is it lysine? Sometimes you get confused, right? But if you're going to remember the structures, so students don't memorize. But if you know that lysine, I know lysine is a basic amino acid because it has an additional amino group located attached to your epsilon carbon. So if you have two amino groups, you know that an amino group can be protonated to plus, right? NH3 plus. So your lysine can potentially have a charge of plus 2, right? So there you can answer it easily. So if you're going to add your hydroxide ion and you're going to remove your hydrogen ion, which of the three functional groups will deprotonate first? Your alpha carboxyl, your alpha amino, or your epsilon amino? There's a slight delay, right? But you know very well that the most acidic functional group will deprotonate first. They will deprotonate first. So this will be our ionic species, right? So from here you can see that your alpha carboxyl has deprotonated, it becomes your carboxylate, right? It's become the carboxylate. Your alpha amino and your epsilon amino do not have to deprotonate yet, right? Because the pH is still low, you have a lot of relatively, you still have an abundance of your hydrogen ion. So in this case, our moiety will be your carboxylate is -1, your alpha amino is still +1, your epsilon amino is still +1. So the charge here is +1, right? You cannot go immediately to 0. Okay, you have to pass to +1. So this is a good question. This is a good question. You keep on titrating. Which of the two will deprotonate first, the alpha amino or the epsilon amino? If you're given, no, if you're given in the exam, you're given the functional groups. You're given the functional groups, right? And in this, your alpha carboxyl is already ionized. Your alpha amino is protonated. Your epsilon amino is protonated. You add hydroxide ion, which will give first, and you're given the pKa values. You look into the pKa values, the one, or even if you may not even be given the pKa values, no, you just have to have an idea. The pKa value of your epsilon amino is higher than the pKa value of your alpha amino, right? So the pKa value of your alpha amino is lower, so it is more acidic. It will deprotonate first. So if we're going to look at this, your epsilon amino maintained, right? Because your alpha amino is more acidic, right? Very good. Very good, no? So Jacobs, Cantaroni, John Beltran, Ralph Lauren, Kaiser. Very good. Okay. So in this case, no, you follow the route of increasing pKa values. Okay, the lower the pKa, the more acidic it will be, the one that will give off your hydrogen ions first. So the charge here is you have -1, you have +1, you have neutral, so they cancel each other. It is zero, right? This is zero, and what do we call this? A doubly charged PC with a neutral, with an overall charge of zero. That is your sweeter ionic. Okay, that is your sweeter ion. That is your sweeter ion. Very good. So you keep on. No, you can still move on. You can still go on because you still have one functional group that can deprotonate. So you have very high. Okay, your pH is now more than 11, more than 10.5. So 11, 12. What happens now? Your most basic group, or your least acidic group, your epsilon amino, will have no choice but has to let go. It has to let go. So now what do we have? What is our ionic species? Look, no, at our ionic species at very, very high pH, your carboxyl group will be deprotonated and your amino group will be deprotonated. So we can see it here, right? We can see it here. Your carboxylate, your alpha carboxyl is negative. Your alpha amino and your epsilon amino are both neutral. So that is negative. That is -1. Again, so just to make it easier to remember, what can have a potential charge of -2? What can have a potential charge of -2? Aspartate or lysine? Just remember the functional groups, right? Your aspartate or even your glutamic, right? Your glutamic or your cysteine or your tyrosine, because of their additional functional group that can become negative, right? That can deprotonate and become negative, like your sulfhydryl group. It can have a potential charge of -2. But if you're asked which of the following can have a potential charge of +2, think of lysine, because of your two amino groups that can be protonated, and each can carry a charge of +1. Your three basic amino acids, your histidine, your arginine, and lysine, can potentially have a charge of +2. Okay, so pKa and pi the same. pK1, pK2, and pK3. pK1 is the pH where you have exact concentration, or 50% of your +2 and 50% of your +1. So this is the greatest buffering. Okay, you have a plateauing. Okay, you can, because of based on the principle of buffers, right? The relationship between your acid and your conjugate base of the acid. So same here. But look at this, okay? The PI now is not here, no? The PI is not the average of your PK1 and PK2, no, because it makes sense. Again, the PI, or the isoelectric pH, is the mean of the pKa values on both sides of your sweeter ionic. Okay, on both sides of your sweet ionic, your +1 and your -1. And for basic, just remember, basic, the pH is high, right? So just remember, the pi of your basic amino acids is the average of the two most basic functional groups. If it is basic, the pH is higher, right? So it's pK2 plus pK3. pK2 plus pK3. Okay, this my last slide. Let's do some exercises, Doc. What happens if you have a peptide? What happens if you have a peptide? You know what happens if you have a peptide? I'm sure you have discussed your peptide bond formation. The peptide bond is what? It's a special amide, right? It's a special amide bond between the carboxyl group of one amino acid and the amino group of another amino acid. So if the functional groups, your alpha carboxyl and your alpha amino, have participated in the peptide bond, they don't anymore contribute to the ionic property or the ionic capabilities of your peptide. Let's look at an example. So I'm sorry, I hope it's clear. I hope it's clear. Um, I should have made it bigger, no, but look, what will be the overall charge of the peptide? Now, so this is your peptide. This is your peptide. I'm just going to look at. I'll just going to. I hope you can see. No, if you're using a laptop, no, it will be bigger. But on an iPhone, it might be hard. I apologize. But you have 1, 2, 3, 4, 5, 6, 7. No, you have a heptapeptide. Okay, you have a heptapeptide. So the first amino acid is serine. What is serine? Serine is a hydroxylated amino acid. Serine is neutral, acidic, or basic. Wala siya sa 7. It's not included in the 7, right? So serine is what? Is neutral. Is it polar or non-polar? I know it's hydroxylated. So serine is a polar, neutral amino acid. It does not ionize. The R group does not ionize. Okay. So that's a serine. Next is your histidine. Okay, histidine, you have your imidazole. I know, Hal, no? That's basic, right? Then the third is cysteine. Cysteine is slightly acidic. No, you have your sulfhydryl group. So students, please remember the functional groups. They can really help. No, if you don't know the functional group, you just have to guess. You just have to guess for the right answer. Anyway, methionine is one of the most hydrophobic, one of the most bulky amino acids. No, so it's hydrophobic. It does not have it's difunctional. Glutamic acid is the second most acidic amino acid. No, it has your alpha, beta, gamma. No, it has your gamma carboxyl. Leucine is a branched chain amino acid. It's neutral. It's non-polar. Okay, neutral, non-polar. It's essential. It's one of the branched chain amino acid, and lysine. Okay, so my point here, the carboxyl group and the amino group that have joined in the peptide bond formation will not participate anymore in contributing to the charges. Okay, what will contribute to the charges will be the terminal amino group, the terminal amino group, and the terminal carboxyl group, aside from the R groups that might ionize. Okay, so please remember, students, it's A to C, A to C, amino to carboxyl. No, just follow the alphabet. Okay, amino to carboxyl. So look at this. 1, 2, 3, 4, 5, 6, 7. Which of the following amino acids will have a functional group, will have a third functional group that will participate in contributing to the charges? We know that serine, although its alpha amino group will participate, your OH will not. No, but in hydrogen bonding, no, it's only polar, but it does not ionize. The R group does not ionize. Histidine, we know. Histidine, you have your imidazole group. Imidazole group is basic. No, this can be protonated, so it can become NH positive. Okay, so histidine, it is a third functional group. Here, no? Okay, so histidine, you have a third functional group, that's your imidazole. Then cysteine, we know that cysteine is acidic, right? It's your sulfhydryl. So your sulfhydryl group can participate in contributing to the overall charge. Methionine, we don't have any problem. Methionine is neutral, nonpolar. Glutamic acid, you have your gamma carboxyl. It will participate, right? As just like in aspartic, the alpha carboxyl alpha amino no more. No, what will contribute will be the ionizable R groups. Leucine is a branched chain amino acid, neutral, non-polar. No, it will not participate. Then lysine will have two groups that will participate. First, the alpha carboxyl. Then second is the epsilon amino. Okay, so it's looks complicated, right? Looks complicated. Anyway, let's try. Let's try to we can do this. We can do this. So here are the pKa values, no? So please remember, if it's not given, the pKa value of your alpha amino is around 9. The pKa value of your alpha amino is around 9. The pKa value of your alpha carboxyl is around 2. Okay, then I'm sure your professors will not ask you to memorize. No? This will be given. Okay, this will be given because questions like this usually this for a long time, right? For group discussions. But in the exam, they can just get one. No? You can just get a snippet, no, a snippet of the problem and ask. For example, at pH 6, now what will be the charge of your functional group sulfhydryl, right? Okay. Anyway, so the imidazole I mentioned, your histidine is important in buffer systems because the pKa of your imidazole group is near 7. Okay, please do remember that. So it's 6. Your cysteine, this is a little contrary to what we believe. Okay, we know, doc, cysteine is acidic, right? But why is the pKa of your sulfhydryl group above 7? No, it does not follow. Okay, it does not follow that that functional groups with pKa above 7 is automatically basic. No, 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 no. It does not follow. Okay. Look at the structure. SH cannot anymore accept a hydrogen ion. It just donates, right? So your sulfhydryl, your cysteine is weakly acidic. So it's 8.4. Gamma carboxyl, just like your beta carboxyl of aspartic acid, right? This is acidic. No, it's acidic, right? It's the second most acidic, if I'm not mistaken. Okay, the most acidic is your alpha carboxyl. The next is your beta. Then this is your gamma carboxyl. Then your lysine. Look, your epsilon amino is 10.5. Your alpha carboxyl is 2. Okay, so are we ready? Look at this. If the pH is 1.5, more or less we don't have any problems. 1.5 is very low, right? 1.5 is very low. So most probably we can expect that the carboxyl groups will be undissociated, right? The carboxyl groups will be protonated 1.5. That is below all the pKa values. pH of 1, pH of 1.5 is even below the pH value of, or the pKa value of your alpha carboxyl. So we can expect your COOH groups will be undissociated, and we can expect your amino groups to be protonated, right? So we don't have any problem. So your alpha amino, if your alpha amino is 9, right? And the pH is way, 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 way below. So we expect your alpha amino to be protonated, right? So it's NH3 positive. Okay, so it's +1. I know the reaction will be delayed, right? But I hope you got that. Okay? I hope you got that. No problems, right? So just remember, if the pH is less than pKa, right? It's undissociated, protonated, right? Look, imidazole is the pKa of your imidazole group is 6. The pH is still very, very low, right? So we can expect that your imidazole is protonated. So the charge is +1. Again, if you have a lot of hydrogen ion, expect the basic groups to be protonated and have a charge of +1. The acidic functional groups will be protonated and it will have a charge of 0. Okay, they're undissociated. SH, no, your SH, look at this. This is acidic, 8.4. That's the pKa. The pH is 1.5. So relatively, you have an abundance of your hydrogen ion, right? So your SH will not protonate. It will be protonated. So the charge is 0, right? The charge is 0. Makes sense? Your alpha carboxyl in the same vein, it's 4.1. The pH of the milieu is 1.5, so you have relative abundance of your hydrogen ion. Your gamma carboxyl, although it's acidic, will not will, does not have to dissociate, right? It does not have to deprotonate, right? So it will still be 0. I hope you're getting. I cannot gauge the reaction. Okay, I cannot gauge the reaction, but I can see. I hope I can see you nodding. Okay. Anyway, your epsilon amino, this is very, very basic, much more. Now, very, very basic, 10.5, 1.5, we can expect this to be You have a lot of hydrogen ion concentration, a lot. So your epsilon amino will be protonated. So this will have a charge of +1, right? Then last, your alpha amino, although it's the most acidic, no, it should be giving hydrogen ion, right? But the pH is still below, right? The pH is still below pKa, so we can expect your alpha carboxyl to be undissociated or to be protonated. So it's 0. So the charge here, the total is +1, +2, +3, +3. So students, okay. So if you don't want to think anymore and you can see that the pH is very low, one tip, choose an answer that is very positive. Okay, choose an answer that is very positive. Most probably you're giving you're making an educated guess. If the pH is low, your hydrogen ion concentration is high, you have a lot of charges that are positive. Okay. If gets to down to the wire, no, you, cannot think anymore. Just make an educated guess. If the pH is low, you choose a choice wherein it's very positive. It's very positive. Okay, look at this. Pay attention. No, we're titrating. No, we're adding sodium hydroxide. In other words, we raise the pH to 6. You raise the pH to 6. Oh, saan ba? You raise the pH to 6. Your alpha amino group is 9. Your pH is already 6. Now, this is still below. Relatively, you still have a lot of hydrogen ion concentration, so your amino group will still be protonated +1. But look at this. What did we say again? So pay particular attention. 6. The pH is 6. The pH is 6. The pKa is 6. What do we say again? What do we say again if the pH coincides to a pKa value of a functional group? What did we say? If your pH coincides to a pKa value of a functional group, you'll have 50% of both species. So you have 50% of 0 and you have 50% of +1. In other words, you have 50% of the protonated imidazole and 50% of the, deprotonated imidazole. So the charge of your imidazole group here is 0 plus 1 divided by 2, it's plus 1 half or plus 0.5. That should be plus 0.5. Okay, plus zero point 0.5. I hope you're getting. Now you just rewatch. Okay, rewatch this video. You rewatch this video again to explain the pH. No, this is the pH. This is the pH. No, this is the pH. The question, and this is the pK values. Look at this. The pH corresponds to your, very good, Ralph. You got it. You got it. The pH corresponds to your pK value, right? So what did we say again? If the pH is equal to the pKa value, you have 50% of the protonated imidazole, that is +1, and 50% of the deprotonated imidazole, that is 0. So 50%, 50%, 0 plus 1 divided by 2 is zero point 0.5, right? Right, Ralph. Very good. Okay, so that's zero point 0.5. So pay particular attention. Another tip, another tip. If you can see a pH value that coincides to a certain pKa value, again, if you can see a pH value that coincides to a pKa value, the answer is not a whole answer. The answer is not a whole answer, it's a fraction. So among the choices, if you only see one fraction, that's the answer. Okay, so make an educated guess. But if you have two fractions, that it will depend on the charge. Okay. So look at this. No, the sulfhydryl group is 8.4 and it is 6. So relatively, what can we say? This is still high, 8.4, and this is 6, right? So your sulfhydryl group will still be undissociated or will still be protonated. Do you get that? 8.4 and 6. Now you always compare the pH to the pKa. Make the pKa your benchmark. Make the pKa the benchmark. The pKa is stable, it's constant. It is the pH that changes. Okay? It is the pH that changes. So in this case, the pH is lower than 8.4. So relatively speaking, you have a lot of hydrogen ion. Your sulfhydryl group is still protonated or undissociated or unionized. So it's still SH, now it's neutral. Look at this. The pKa of your gamma carboxyl is 4.1, but the pH of the milieu, of the surrounding milieu, is 6. So it is higher already. It is higher already. So you have a relative scarcity of your hydrogen ion. Your gamma carboxyl will be deprotonated or will be dissociated. So it's -1. Okay, that's -1. Your epsilon amino, very, very high pKa. Now, very basic. Your epsilon amino is one of the most basic. But the most basic is your guanidinium, 12 something, no? Guanidinium. Your epsilon amino of lysine comes close. No? It's still very basic. 10.5, 6. Okay, so relatively speaking, you have a preponderance, you have an abundance of your hydrogen ion. This will be protonated, so +1. Alpha carboxyl, this is clear. Your pK is 2, your pH is 6. So the pH is very, very above. Okay, it's above your pK value. So in other words, you have a scarcity of your hydrogen ion. Your alpha carboxyl will ionize or is deprotonated, -1. So if we're going to add, this cancels out. This cancels out. The charge is still plus one half. Okay, plus one half or plus zero point 0.5. Plus zero point 0.5. Okay, so plus zero point 0.5. So it is still cationic. It will migrate to the cathode, to the negatively charged. Okay, to the negatively charged pole. 7. 7. So that's the neutral pH. Let's make this fast. No, I apologize. It's almost 1.5. So 9. pKa of your alpha amino is 9. This is 7. So in other words, this is still lower, right? This is still lower. Your alpha amino will still be protonated. So it's +1. Look here. 6. The imidazole group is basic, no? It can either be protonated or deprotonated, but the pH is already above the pKa. So your imidazole will be deprotonated and the charge will be 0. Okay? I hope you get that. No, the pH is higher than the pKa. pH is higher than the pKa. So you have relatively scarcity of your hydrogen ion. Your imidazole group will deprotonate. Your SH is 8.4, but still your pH is lower, still lower than your 8.4. This does not have to ionize still, so this will also still be 0. It will still be 0. Your gamma carboxyl is 4.1. This is way, way above. So this will be deprotonated, ionized, or dissociated. So this will be -1. Your epsilon amino, 10.5, very high, very basic. The pH is still below your pKa. So in other words, you still have an abundance of your hydrogen ion. This will still be protonated. This will still be protonated, so it's +1, right? Okay. Then this is it follows, right? The pH is already high. Your pK is 2, so this will be dissociated or deprotonated, -1. And look, 1 plus -1, 0. 1 plus -1, 0. The charge is 0. So in other words, at neutral pH or near neutral pH, the amino acids or peptides will have a charge of 0. No, most not all the time. Anyway, you have nuances. So where will it go? Where will it migrate? It will not move. Okay, the heptapeptide will not move. Okay. Next, now if we increase the pH to a very high, 10.5. Look now, your pH already surpassed the pKa of your alpha amino. Already surpassed the pKa of your alpha amino. So your alpha amino will deprotonate. So instead of being NH3, it will now become deprotonated and NH2 without a charge. So it is 0, right? It is 0. Follow? Then 6, imidazole, no, just like this, no, it will not be protonated anymore. No, 7, it's not protonated anymore, much more at 10.5. So scarcity of your hydrogen ion, this will not be protonated. No, it's NH, it's N or NH, no, it's 0. Your sulfhydryl group, 8.4, 10.5. Look, what do we see? What do we see here? 8.4, the pK is 8.4, but the pH of the milieu is 10.5. So in other words, the surrounding, no, the surrounding will have a relative scarcity of your hydrogen ion. Your sulfhydryl group will have no choice, no, although it has a high pKa, but to what, no, to let go. to deprotonate or to dissociate. So the charge here is negative 1, negative 1. Gamma carboxyl is also negative 1 because no 10.5, 4.1 relative scarcity or paucity of your hydrogen ion. So it is negative 1. Here again, look closely. The pH is 10.5. The pKa of your epsilon amino is 10.5. The pH is 10.5. So what do we say? What do we say? What do we see? What do we see? The pH is coincidental with your pKa. So you have what? You have 50% of the protonated NH3 positive and 50% of the deprotonated NH2. The charge here is plus 0 plus 1 is 1 divided by 2 is plus 1 half. Is plus 1 half. Okay? Your alpha carboxyl 2, very, very low pKa, but your pH is 10.5. So definitely this will be negative, negative 1. So look, negative, negative, negative is negative 3, negative 2.5, no? Negative 2.5. So takeaway message, at very, very low pH, the peptide will most probably be positive. It will be cationic. It will migrate to the cathode. Okay? At very, very high pH, no, 10.5, 12, no, it might be extreme 13. Your carboxyl groups will be deprotonated, will be carboxylate. Your amino groups will be deprotonated, will be NH2 neutral. So at very high pH, the polypeptide will most probably be negative. So that will cut down your choices, okay? If you see extremes of pH, that will cut down your choices. However, an additional takeaway message, if the pH is coincidental with the pKa value of any of the functional groups, you can bet that the charge will be a fraction. It will not be what? It will not be a whole number. Okay? So that's that. I hope you learned something. I think no, you can ask questions. No, that's my last slide. So thank you very much. AMS Bondok, John Beltran, Kentaroni Oyama. If you haven't subscribed yet, kindly subscribe and share this video to your classmates or to your friends who might benefit. Okay, who might benefit in this live stream, in this video. Do you have any questions? I'm willing to answer any of your questions. I hope I was clear. Okay, I hope I was clear. I know this is a highly contentious topic, right? Highly contentious topic. You can ask questions. Um, so in the quiz with 1 minute per question, they'll not ask like this, like fill in the table, but they can get snippets. Huh? They can get snippets. Thank you very much, uh, John. Okay, very very appreciated. Cantaroni, you're welcome. You're welcome. You can see this will be recorded. No? This will be recorded and will stay put in YouTube forever. No, you can share. And if you have any topics, no, you can. If you have any topics that you want me to discuss by live stream, no, you just comment in any of my videos. Doc, is it possible to have a negative charge? Yes, yes. Jacobs, like this. Very good question. No, very good question. Uh, if if the pH coincides with the pKa of your beta carboxyl or pKa, if if the p like this, is it possible to have a negative one of charge? Not for the whole. It might be complicated, but for the functional group, the functional groups of the acidic amino acids, for example, your beta carboxyl, okay, your gamma carboxyl, your sulfhydryl, your sulfhydryl, your phenyl hydroxyl. If the pH corresponds to their pKa, the charge for that functional group will be negative one half. Jacobs, did you get that? Did you get that? I should have put an example. In this case, look at this. Um, you have plus one imidazole because imidazole is a base, right? A base. It can only have a NH2 or NH3 positive. Epsilon amino the same. Epsilon amino the same. However, if the pH is equal to the pKa of any of the four acidic amino acids, so beta carboxyl, your gamma carboxyl, your sulfhydryl, and your phenyl hydroxyl, the pKa value for that functional group will be negative one half. Good question, Jacob. I know. The question is that, Doc, is it possible to have a negative one charge? Yes. If the pH is equal to the pKa of an acidic third functional group of an acidic amino acid, specifically beta carboxyl, gamma carboxyl, sulfhydryl, and your phenyl hydroxyl. Welcome, Kenneth. Thank you. Please, yes, I am. I will. I will. Okay. So kindly share. kindly. I'm trying to pay it forward as well. Okay. I've taught biochemistry for 25 years now. I retired. Okay, and I keep on. No? I keep on teaching. No, although I'm not teaching classes in small group discussions anymore now, but I leveled it up. Okay, brought it to the web, to YouTube. Thank you. You're welcome, Jacobs. Okay. So, any more questions? So I hope you, for me, even one, if only one is watching, that's enough. Okay, if I can only help or teach or touch a student, that is enough gratification for me. Okay, so again, thank you very much. S- Uh, uh, Okay, welcome, Ralph. I hope, and I do appreciate the kind words. Okay, I'll be ending the broadcast if there are not no any more questions. What else? Please do remember, the question might be, um, the question might not directly ask you what will be the overall charge. No, it can be dressed differently. For example, to which what will happen if subjected to electrophoresis? This polypeptide chain will migrate, not move at all, migrate to the cathode, migrate to the anode, or all of the above. So for me, the easier way for that is, if look at the pH. If the pH is very low, it will be most probably be cationic and migrate to the cathode. Again, remember, if you're confused, Doc, what's the cathode? Is that the positive or is that the negative? Just remember the pole is named after the ion. So if it is a cation, it will move to the cathode, which is the negatively charged pole. Okay, if it is an anion, no, you have negative charges that predominate, it is an anion, it will migrate to the anode that is positively charged. Thank you very much, Janelle. I appreciate that, and thank you for for sticking around. No, 1.5. That's quite long, but this is a complicated subject. Okay, so welcome and thank you very much as well, Janelle. Any more questions? What else? What type of questions? Sometimes like this. Which region will give the greatest buffering capacity? Then you're given different pH. Um, just look at the pKa values. Okay, the pKa values. Or if you have a titration curve and you have point A, point B, point C, point D, look at the points wherein you have a plateauing. Okay, you have a flattening of the flattening of the curve, parang COVID. So you have a plateauing. If it's a plateauing, then that's the region of the pKa. That's the region of the greatest buffering capacity. Pi theoretically, your isoelectric pH, because it's the average of your pKa values. So isoelectric pH theoretically will have the least buffering capacity. Just when you add a little acid or a little base, the pH will change dramatically, in contrast to the pKa values. Okay, so I think I apologize. No, the stream took a lot of your time, but hopefully this can help. Don't memorize. Again, I keep on emphasizing the classification. The classification. Don't memorize the classification. I know you have a lot of mnemonics for polar, non-polar, neutral. Just remember the four acidic, the three basic. That's seven. If you want to level it up, no, level it up. Remember the four polar neutral amino acids. The two hydroxylated amino acids, that's serine and threonine. They are polar neutral. They participate in hydrogen bond formation. Same with your amidated amino acids, your asparagine and glutamine. They are neutral, but they are polar, but they don't ionize. Okay. Again, thank you very much to the 20,000 viewers. Thank you very much. I do appreciate that. So I'll be ending this broadcast. Have a great night, and if you have exams tomorrow, good luck, and always stay safe. So I'll say goodbye in 3, 2, 1.